Hello. Having discussed both explicit and implicit methods for parabolic PDE and also discussed about the local truncation error and then how to estimate it for a particular approximation, we must discuss more of these approximations. So, what are the properties any approximation, any method should have? What kind of main features we have to pay attention? So, the main features are consistency, stability and convergence of a particular approximation. So, when I say consistency, stability and convergence, which comes first? So, there could be a debate, but in general when we talk about any numerical method, people immediately talk about convergence, whether your method converges or not. Okay. So, maybe this is more intuitive, so immediate concern for us. So, let us start with convergence. Okay. So, what do you mean by convergence? So, for example, we come across several incidents where the convergence has to be talked about. So, when do you say something converges? So, for example, in this context we have approximated the corresponding PDE by a particular finite difference method. So, then we are solving. So, the solution obtained should converge to the original solution, that is the exact solution of the equation. Okay. So, let us put down formally and then proceed further to talk about consistency and stability. Okay. So, the title I put consistency, stability and convergence. Okay. So, as I mentioned, I would like to talk about convergence first. So, as I mentioned briefly, a one step so we need a formal definition, that is why I would like to put down here a one step finite difference scheme approximating a PDE is a convergent scheme if the solution of the finite difference scheme, say call it Uij, converges to U of x t, which is any solution of the PDE as delta x delta t goes to 0. So, this is a formal definition. So, one step finite difference scheme approximating a PDE is a convergent scheme if the solution of the finite difference scheme Uij converges to the exact solution, which is any solution of the PDE as these parameters goes to 0. Okay. So, once as I mentioned, once we talk about the convergence, there are two more, you can see stability and consistency. Okay. So, even consistency, if you see consistency, for example, when you talk about stability of a method, see suppose somebody is little perturbed, it is okay, but somebody is more perturbed, then definitely we say the person is not stable or the system is not stable. So, that means it is a general usage, and even in this context as well it is the same. So, in the sense, if you give small perturbations and then if the small perturbations remain small, then there is no issue. However, if the small perturbations grows up and then blows up, so then definitely the particular system is not stable. Okay. So, let us see the formal definition of stability. Stability. So, the error caused by a small perturbation the numerical method remains bounded. So, the error caused by a small perturbation in the numerical method remains bounded. Now, for a specific method, this could happen independent of any conditions. However, for a particular method, this could happen subject to some conditions. Okay. So, the remarks. Okay. So, this could happen unconditionally the entire domain of definition, or conditionally within a range. Okay. So, we will when we come to a specific method, we talk about this. Okay. Then the next, consistency. Given a PDE LU equals to F, approximated by say Lij equals to F. Okay. Then the finite difference scheme Lij u equals to F is consistent with the PDE if L psi Lij psi goes to 0 as delta x delta t goes to 0 for psi smooth enough. So, that means, let us have a understanding. Given a PDE L equal to F approximated by this, then the finite difference scheme Lij equal to F is consistent with the PDE if L psi minus Lij psi goes to 0 as this parameter goes to 0 for psi smooth enough. Okay. So, now what could go wrong? What could go wrong? So, that means a scheme approximating a PDE may be stable, but has a solution that converges to the solution of a different PDE, different equation as the so this is inconsistent. Okay. That means scheme approximating a PDE may be stable, but the solution converges to some other PDE, okay, as the mesh length goes to 0. So, this is inconsistency. Okay. So, let us consider an example. So, let us say our operator is first order for the time being. Okay. Then L psi is okay. Then L I j say forward space, forward time. Okay. So, accordingly we get L I j to be, so forward space, forward time. Okay. So, we get psi j plus 1 j by delta t plus constant times forward space. Okay. So, this is our L I j, right. So, now in order to compute the error, we have to expand in Taylor series. Okay. So, let us expand psi I j plus 1 so this is evaluated at okay. T square again evaluated at this point, okay, plus. So, similarly okay. So, this we have done number of times. So, now if we substitute, okay, then L I j psi is L I j psi becomes, we can just straight away substitute. Okay. So, for example, you can see this sitting here. So, this get cancelled. So, first term here delta t also cancels. So, first term is dou psi dou t, and here this term cancel with this, delta x cancel with this. So, first term here a times. Okay. So, this is just an algebra. So, if we do that, we get can verify. So, this is a misuse of notation, we could have written simply one big O. Okay. So, therefore, L psi minus Lij psi equals to, so this is exactly, so this will be okay. So, which goes to 0 as so therefore, scheme is consistent. Okay. So, the scheme is consistent. So, now we should talk more about consistency, stability, convergence, what is the interplay among these three properties. Okay. So, there is an interesting theorem in numerical analysis which talks about this. However, there are some restrictions in order to apply this theorem. Okay. So, let us see which ensures what. Okay. So, the theorem is Lax Richtmeier equivalence theorem. Okay. So, this also called fundamental theorem of numerical analysis. Okay. So, before putting the statement, the net gist of this consistency plus stability, both sides I am putting consistency, stability ensures convergence, convergence ensures consistency and stability. This is the gist of this theorem. Okay. However, as I mentioned, there are some restrictions. Okay. So, let us put down formally of a linear finite difference scheme is consistent with a well defined linear IVP, that is the initial value problem, then stability guarantees convergence as mesh length goes to 0. Okay. So, this says if a linear finite difference scheme is consistent with a well defined linear IVP, then stability guarantees convergence as mesh length goes to 0. Okay. So, a method that is consistent and stable convergence is guaranteed, but In general it is both ways. However, the main restriction is, the remark is linear. So, this is quite important, because in general people look for nonlinear, because several of the challenging problems involve nonlinear stuff. However, this is restricted to linear problems. Moreover, consistency, stability, ensuring convergence is trivial in some sense. However, the theorem assures the converse, convergence implies consistency and stability as well. Okay. So, let us proceed to a little complicated example, okay, the second order, so that we get some idea. Let this be approximated by so from delta t I am using k. So, you may be thinking every time the same example. So, for a change we have gone to a different example, you can see. So, this looks little heavy, let us see how we proceed. Okay. So, the story is the same, we have to expand in Taylor series and collect the coefficients, etcetera. Okay. So, let us consider term by term. So, this is one term and this one term and this is another term for me. Okay. So, u I j plus 1. So, this if you consider u plus k du dot t So, I am dropping the evaluation at x I t j, okay, it is understood. Minus u okay. So, this become, so you get cancelled, you get 2 k, right, then this k square by 2 with a negative sign, this get cancelled. So, the next term by 3 here actually. So, there is this should be 3. So, then the next term okay. So, the next so, if we consider this, So, this is just a labor. Alternate signs. Okay. So, ultimately we get this is j plus 1. So, this all should be t there, apologies. Yeah. So, this is 2 u and all this k. Okay. So, k then okay. So, then we are left with 2 more terms, this and this. Okay. So, that also we can compute. So, having done so many times, we can guess. So, there will be u and u that cancels, and here with the plus h and minus sign, and here with a minus h. So, it will be 2 times. Okay. Okay. So, we get, so there is a, this is a plus sign. So, then u that will be 2 u, then plus h minus h they get cancelled, plus h square term becomes twice. So, h square by 2 is twice, then cubic term cancels. Okay. So, now using all this, T I j become minus 1 over h square So, I am giving only few terms. So, this is an important exercise. So, even though there is some labor involved, better to do this. So, this I am clubbing, you can see. So, this get cancelled. So, h square cancels. So, you get dou e by dou t minus this term. Okay. This is what I put. Then the next term I am going to put is this one. Okay. Then the next term is this. Then I am putting this. Then we have this term, etc. Okay. Now, case 1, see, even though we clubbed these terms because this is our actual equation, but unfortunately there is one more term with the first derivative, okay, first derivative with respect to t, right. So, we have to analyze carefully. Suppose k is lambda h. So, lambda is our grid parameter, say k is lambda h. So, then Tij reduces to plus k is lambda h. So, you have lambda by h plus 2 lambda square, okay, 2 lambda square, k is lambda h. So, you have one term. So, let me check. Yeah, so k is lambda h. So, you have this, okay, then etc. Okay. Now, as h goes to 0, so this is troublemaker, okay, because as h goes to 0, okay, this is not getting absorbed in this. Okay. So, therefore, inconsistent. Okay. Therefore, it is inconsistent. Okay. Suppose case 2, k is lambda h square, then T I j so this goes to 0 as h goes to 0. So, therefore, consistent. Okay. So, therefore, in this case the method is consistent, it is agreeing with the original PDE. Okay. So, this test is very much important. If you come across any finite difference scheme approximating a given PDE, we do this test for consistency. Okay. So, now having done consistency check, let us see whether we can discuss about stability of a method. Okay. Stability and convergence. So, convergence via differential equation for the error. So, this is called direct method. Okay. So, consider, so I am putting a bar just to make sure that this is exact. Then initial condition, so u bar is given, then boundary condition u bar some a t is given, u bar b t is given. So, in this case a equals to 0, b equals to 1. Okay. So, this is for all t. So, now consider finite difference approximating star by u I Okay. So, now we would like to talk about convergence, right. So, what would happen at each grid point, there will be some error. Okay. So, at mesh points, this is a discretized and say this is exact, they differ by this is the error. Then following this ansatz, etc. Okay. So, now consider our scheme. Substitute this in this scheme, we get, so left hand side u I j plus 1 minus u I j. Okay. So, we have our, so you can convert this into equivalent form. So, that will be u I j plus 1 equal to lambda u I minus 1 j plus 1 minus 2 lambda. This is our standard form. Okay. So, then let us substitute these answers. Okay. So, then what will happen? We get here u I j plus 1 minus. Okay. So, we retain error to the left hand side, we get lambda, then plus the exact solution we get this. Okay. Now, our aim is to get an equation for the error and then estimate the error and see whether we can make it bounded whether conditionally or unconditionally. So, that we talk about the convergence, okay, and the stability. So, now using Taylor series, which is a only first term I am writing. So, this I will put it as an error term x I plus some theta 1 h. So, this is the error term. Okay. So, this is evaluated at x I t j. So, then this is Taylor's remainder term. Okay. Then say some theta 3 k. So, h is increment for space and k is increment for time. Okay. So, where this is standard Taylor's remainder conditions. So, then using this in our error equation, plus k times okay. So, where okay, from these two we get this. So, this is double star is a difference equation for E I j. Okay. So, this is a difference equation for E I j. Now, let E j is max of E I j. So, that is at jth level and m is max of okay. Then if you carefully observe, so we have 1 minus 2 lambda. So, therefore, for lambda less than or equals to half, coefficients of E I j in double star are positive or 0. This is an important remark. So, therefore, So, for this we need a positive or 0, because we need an estimate. Okay. So, therefore, for this range coefficients positive or 0. So, therefore, mod of this is less than or equals to lambda mod E I minus 1 j plus 1 minus 2 lambda j plus lambda plus k m. How we are getting? Carefully observe. So, let me repeat. So, we have considered the ansatz. This is approximated with exact, differ by an error, and at each grid point we play with the index. Then this is our difference scheme. Okay. Then you substitute this ansatz in the difference scheme. So, we get this. Then we expand in Taylor series, and substituted back. So, we get this. So, now this is a difference equation for E I j. Now, let at jth level the maximum error, because at each grid point the error is different. So, the maximum is E j, and correspondingly you call this. So, now we are estimating the bound. So, this is we called already m. So, therefore, we get so this E j j j So, this is right. So, now we have obtained. So, we have obtained so this is less than or equals to E j plus k m, and this which is true for every I, hence true for max So, therefore, so max is not E j plus 1, are you getting? So, this is true for every I. So, therefore, true for max. So, which is nothing but capital E j plus 1. So, this is E j plus k m. Now, you iterate So, this if we do so here 2 times, so we get 3 times. So, so on if you do. Now, what will be this? Any idea? E 0 error at t equal to 0. So, there is no error and j k is t since this, okay. Then this is T m, okay. So, further when h goes to 0, k is lambda h square goes to 0, m goes to at I j, this also goes to 0, okay. So, therefore, m goes to 0. So, therefore, E j plus 1 goes to 0, that means any E j, okay. So, as E j, this implies u goes to u bar as h goes to 0 when lambda is less than or equals to half and t finite. So, this is our net conclusion, okay. U is agreeing with the exact only when lambda is less than or equal to half. So, the remark is when lambda greater than half, the error blows up. You can verify. So, in this case, okay. So, this is conditionally that means the error is not growing. So, therefore, it is stable, okay, only in this range. So, this is called conditional stability. Okay. Suppose you do not get any condition and then we say it is unconditionally stable, right. So, we estimate the bounds, the domain in which the method is stable by using this error answers. Okay. So, that means we formulate the corresponding differential equation corresponding to a given finite difference scheme and then we find estimates and we find the domain within which the method is stable. Okay. So, we discuss more there are other methods to talk about stability. So, we discuss in the coming lectures. Until then, thank you.